Have you ever sent a photo online and wondered how it actually gets to the other side? Let's send a photo of the Mona Lisa through the internet and see how it travels. Let's take the journey with Mona Lisa as she makes her way from server to screen through the internet, bouncing between routers and cables. In reality, the client initiates a request for a particular resource from the server. Then a TCP connection is established for the reliability of the process. Let's assume that the connection is being already done. The internet is a vast web of countless routers, all working together to move data across the globe. But for simplicity, we'll shrink it down and mimic this complex network with just 8 routers. Let's see how they help deliver the Mona Lisa to her destination. Every device in a network has its own unique identifier, called an IP address, like a digital home address. In our example, the server's IP is 192.168.1.10, while the client has the address 10.0.0.5. These numbers will guide the Mona Lisa on her journey across the network. Every computer has 7 distinct layers that work together to send data. The image starts its journey at the upper layers, then reaches the transport layer. It's divided into segments, and it also adds headers to ensure reliable delivery, sequencing, and acknowledgement, and then it's sent to the network layer, where it's broken down into smaller pieces called packets. Each packet, usually around 1,500 bytes, is carefully sized to fit within an Ethernet frame. Each IP packet contains a header and a fragment of the image data. As we dive into the details of an IP header, let's break down its key elements with this diagram. Version specifies the IP version being used, usually IPv4 or IPv6. Header length indicates the length of the header itself. Type of service prioritizes the packet's delivery based on the service type. Total length the entire size of the packet, including the header and data. Identification used to help reassemble fragmented packets. Flags controls whether the packet can be fragmented. Reserved bit always set to 0, unused. Don't fragment, DF. If set to 1, the packet cannot be fragmented. More fragments, MF. If set to 1, it indicates that more fragments follow this one. If 0, it's the last fragment. Fragment offset helps in reassembling the packets in the right order. Time to live, TTL, limits the packet's lifespan by reducing its value at each router. Protocol specifies whether the packet is using TCP, UDP, or another transport protocol, in this case, TCP. Header checksum verifies the integrity of the header data. Sender's IP address the IP address of the sender, in this case, 192.168.1.10. Receiver's IP address the IP address of the receiver, in this case, 10.0.0.5. Options optional. Extra settings, sometimes used for special purposes. Padding these bytes are added to ensure that header ends on a 4-byte boundary. Together, these fields ensure that the packet gets to the right destination intact and efficiently. Once the server has encapsulated the image segments into IP packets, it needs to send them on their way. But before they can travel across the internet, they first have to reach router 1, the default gateway of the local network. The IP address of router 1 is passed down to the data link layer, preparing the packets for the next step of their journey. Before our packet can hit the road, there's one more important step, encapsulating it in an Ethernet frame. Think of it like putting the Mona Lisa in a special delivery envelope so she can travel safely. At the data link layer, Ethernet steps in to wrap the packet with the information it needs to get through the first leg of its journey, starting with router 1. Now let's take a quick look inside the Ethernet frame. It's like the delivery package for our packet. First, there's the preamble, which helps the sender and receiver get in sync. Next, the start of frame delimiter, or SFD, signals the beginning of our frame. We also need the destination MAC address and source MAC address to show who's sending and who's receiving the data. The ether type tells us what kind of protocol we're using, like IPv4 or IPv6. Then we have the payload, which is the main content, our IP packet. If the data's too small, we add some padding to meet the frame size. Finally, the frame check sequence, or FCS, ensures everything arrives intact, checking for any errors along the way. Here's where things get interesting. The data link layer works with MAC addresses, not IP addresses. So, before our packet can reach router 1, we need to translate the next hop IP address into a MAC address. MAC addresses are unique hardware identifiers, like a digital fingerprint for every network device. They ensure data gets to the right physical machine. But what if the server doesn't know the MAC address of the next hop? That's where the Address Resolution Protocol, or ARP, comes in. The server sends out a request asking, "Who has this IP address?" Let's zoom in on the ARP request and see what's inside this small but powerful message. Hardware type. This specifies the kind of network we're working with. Here, it's Ethernet, so the value is 1. Protocol type. This tells us what protocol is being used. For IPv4, the value is 800. Hardware address length. This is how long the hardware address is. For Ethernet, it's 6 bytes because that's the size of a MAC address. Protocol address length. For IPv4 addresses, the length is 4 bytes. Operation. Here, we've got a 1, meaning this message is an ARP request. It's asking for a MAC address. Sender hardware address. This is the MAC address of the device making the request. Sender protocol address. The IP address of the sender. Basically, "Hey, I'm asking for your MAC, and here's my IP." Target hardware address. This field is empty for now because the sender doesn't know the target's MAC yet. That's what it's asking for. Target protocol address. The IP address of the device the sender is trying to find. All devices on the network will check this against their own IP to see who should respond. Now that the destination MAC address is known, frame can be passed to the physical layer. Now that the packets will be sent to the router 1. Routers use the lowest 3 layers of the OSI model. When a server sends packets, the router receives them at the physical layer, converts them to bits, and passes them to the data link layer. At the data link layer, the raw bits are organized into a frame, which includes the MAC addresses of both router 1 and the server. When router 1 receives the frame, it checks the destination MAC address to see if it matches its own. If the MAC address matches, the frame is accepted and processed further. However, if the MAC address doesn't match, router 1 simply discards the frame. Once the frame is successfully received and verified, the data link layer removes the headers and trailer that were added during framing. This leaves behind the original IP packet, which contains important information for routing. The cleaned-up packet is then passed up to the network layer for further processing and routing to its final destination. Router 1 begins by examining the IP header of the packet. One of the key fields it checks is the TTL, time to live, which helps prevent packets from circulating endlessly in the network. Router 1 decrements the TTL value by 1. If this value reaches 0, the router discards the packet and sends an ICMP time-exceeded message back to the server, notifying it of the issue. However, if the TTL is still greater than 0, router 1 forwards the packet to its next destination. So, the packet is forwarded to the next hop router based on the destination IP address of the client. Each router along the way examines the packet's IP address and decides the best path to forward it. This process continues from router to router until the packet reaches its final destination, ensuring efficient delivery across the network. But how does the router decide which path to take? That's a crucial part of its job, and it relies on routing algorithms to make that decision. We'll dive deeper into how routers choose the best route later on. Now that the packets have arrived at router 8, the final router in the journey, it receives the packets encapsulated within frames and quickly verifies their integrity. The packets are then passed to router 8's network layer, where the IP packet is processed. Router 8 strips off the data link layer header and inspects the IP header, checking the destination IP address. Since the destination IP matches the client's IP address, Router 8 recognizes that this is the final hop. The client is on the same local network, so Router 8 determines the correct interface to forward the packet. The router passes the client's IP address to the data link layer. To complete the transfer, Router 8 re-encapsulates the IP packet into a new data link layer frame. The new frame contains the following: source MAC address, the MAC address of the Router 8, 00:1, A:2, B:3, C:4, D:5, E destination MAC address. The client's MAC address, which Router 8 retrieves using ARP if it doesn't already know it. Let's take 00:1, B:44, :11:3, A:(B7 as the MAC address of the client. Finally, Router 8 sends the frame through its outgoing interface, transmitting it over the local network toward the client, bringing the packet one step closer to its destination. Now that the client has finally received the bits, the journey isn't over just yet. The physical layer collects these bits and passes them up to the data link layer, where they are reassembled into a frame. The frame then moves to the network layer, which processes the IP packets and hands it off to the transport layer for final delivery. Each layer works together to ensure the image arrives perfectly, just as it was sent. The transport layer steps in to ensure everything is in the right order. It checks the sequence numbers of the packets, making sure they're assembled correctly. Using these sequence numbers, the transport layer reassembles the packets like puzzle pieces, creating the complete image. It also verifies each packet for errors using the checksum in the TCP header and manages any necessary retransmissions to guarantee that nothing is lost along the way. Now, the image is processed by the upper layers and reaches the application layer. Whether it's a web browser or an image viewer, the application decodes the data based on its content type, in this case, image JPEG, and voila, the Mona Lisa appears on the screen. The fully reassembled data has traveled through the network and finally arrived at its destination. Our journey ends here. The client has successfully received the Mona Lisa, completing her journey across the network. With the Mona Lisa now perfectly displayed on your screen, let's take a quick look at the magic behind the scenes. How did the routers know where to send each packet? Routers rely on routing tables, maps that guide packets to their destination. Each router checks the destination IP in the packet and uses its routing table to decide the best next hop. Destination IP. The goal, for example, 203.0.113.024. Next hop. The IP of the next router along the path. Interface. The port to send the packet through. Metric. The cost to reach the destination, used to pick the best route. The router uses the longest prefix match to find the most specific path to the destination. It forwards the packet to the next hop, another router or the final destination, until all packets safely reach the client. But how do routers keep their maps updated? They use dynamic routing protocols like OSPF, BGP, or RIP. These protocols help routers communicate, share network changes, and always find the best routes. Some routers might even use static routes, predefined paths that don't change, for extra control. And that's how the Mona Lisa traveled through the network, hopping between routers, guided by smart routing tables, until finally arriving at your screen. Farewell, Digital Explorer. May your journey through the internet's invisible highways fill you with wonder. Until we meet again, keep surfing the waves of innovation.